Hello everyone. Let's study about a dipole in an uniform electric field. Before starting this concept, let's recap as to what is an uniform electric field. An uniform electric field is one in which the magnitude and direction is same, is uniform at all the points. That is, if we take few points here called as point 1, point 2 and a point 3, that is any three random points. At all these points, the electric field would be same in magnitude and direction. Such a field is called as an uniform electric field. You learned that if you have a uniformly charged, infinitely large conductor, the electric field at any point on one direction is given by sigma by 2 epsilon naught. So we can assume that an uniformly charged large conductor will provide a uniform field in any one direction. In this case, let's find out as to what happens when a dipole is placed in a uniform electric field. Let's draw few electric field lines. So let this represent a uniform electric field. Let's assume that we place a dipole in this field such that the minus charge is on this side, plus charge on this side. That's what we would get when you place it in this condition. We call this as minus Q, this as plus Q. Let this point be point A, this is point B. So at point B, the plus charge is placed. At point A, the minus charge is placed. Now we learned that there will be force acting on this charge as well as this charge. The force on this charge would be along the field direction. We call this as QE, and the force on this is against the field direction because it is a negative charge, and that force we call as minus QE, just to show that these two forces act in opposite directions. So in this case, the net force would be force on this charge as well as this charge, that is equal to 0. So net force in case of an uniform electric field would be 0. But in this case, a torque acts on this dipole. Suppose the angle here is theta, and also the separation between the two charges is given as 2a by convention. Then on these two charges, net force is 0 but not net torque. To understand this, let's assume a case where there is a force acting on the two sides where the force is same in magnitude and they also have same lines of action. In this case, net force is equal to 0, and also here net torque is equal to 0. But let's take a case where we have similar forces acting on the given point. Let us take a given point where two forces act on this point, but these forces have different lines of action. The line of action of this force is along this, and line of action for this force is along this. So they are different lines of action. In such a case, if the force is taken as F in magnitude, and suppose if their separation is given as X, then in this case also the net force is equal to 0, but the net torque now is not equal to 0. That is because these forces have different lines of action. In fact, the torque here is given as, this is called as a coupled, The torque here is given as the product of any one force into their separation. When I say separation, it means it is the perpendicular distance between their lines of action. So in the same way, if you look at this dipole, the line of action of this would be along this direction and this would be along this line. Now the torque in this case would be the product of any one force and the normal distance between the lines of action. Let's call this as point C. So the torque in this case would be the product of force into BC, because BC is the perpendicular distance between the lines of action. Let's find what is BC first. From this triangle ABC, we can write sine theta as equal to, it is BC because even here the angle is theta only, because these are parallel lines, BC by 2A. Therefore, BC is equal to 2A into sine theta. The torque therefore is given as F, which is just the magnitude of force, that is Q into E into 2 into A into sine theta, and we can rewrite this as Q into 2A into E into sine theta. Recall that Q into 2A is called as dipole moment. Therefore, what we get would be torque is equal to P into E into sine theta. To write in vector form, because torque is a vector quantity, let's go back and look at a diagram. In this case, there will be a clockwise rotation, which means torque acts clockwise. So to get that, the only possibility is to, this is P in this direction, E is like this. If you use the right hand rule, then P cross E would give us torque in this direction. So rewriting this, we can say the torque is equal to P cross E. It is not E cross P, it is P cross E. So this is a torque on a dipole in an uniform electric field. Let's take two cases of it. In terms of magnitude, torque is given as P into E into sine theta. Let's take case 1 where theta is equal to 0 degrees. In that case, sine 0 would be 0, therefore torque is equal to 0. So when a dipole is aligned along the field direction, in that case torque is 0 as well as net force is 0. Let's take a case where theta is equal to 90 degrees. In that case, what happens is the torque would be just P into E, because sine 90 is equal to 1, and this is the maximum torque possible for a given dipole. So we'll write this as torque maximum. This happens when the dipole is placed normal to the electric field such that the angle between these two is equal to 90 degrees. In the third case, we take theta is equal to 180 degrees. Even then, torque is equal to 0. So here, the dipole will be aligned like this, and then the field would be like this, so that the angle between these two is equal to 180 degrees. You can find out what would be the torque when theta is equal to 270 degrees. Just simple max here. So you will find that the torque is maximum for this angle only. That is called as tau maximum. Now let's find out what happens to a dipole when it is placed in a non-uniform electric field. That is, the field could have different values or direction at any given different points. To understand that, Let's draw dipole as drawn in the previous case, like this. We call this as a charge Q. This says at this end charges minus Q. So if you assume a field which is present at these 2 points, but the field is not same in magnitude, let's assume for a minute that there is field acting like this. So the field here is E1, and the field acts at this point also, but the force here would be acting in opposite direction. Let the force on this be Q E2, and the force here would be Q into E1. Just write its magnitude, not with direction. This is what is the value. But here Q1 and Q2 are not same. If we assume that E1 is more than E2, in this case net force is not 0. So the body as a whole will have a translation in this direction. So net force here is not 0. So body will have a translatory motion, and also these two would cause a torque. So whenever a dipole is placed in a non-uniform electric field, this dipole will experience both translatory as well as rotatory motion.